These are the notes for Module 23, where we'll learn about data distributions. First, we get introduced to the normal curve and something that is known as empirical rule. Empirical rule, also known as the 68, 95, 99.7 rule, which says that if you are under a normal curve, 68% of the data falls within one standard deviation of the mean. A standard deviation is a measure of distance. You're measuring the distance from average. So if under a curve, if 0 on this number line represents the average, if you're within one standard deviation, under a normal curve, 68% of the data should fall within one standard deviation of the mean. 34 on each side, 34% above the mean and 34% below. A normal distribution is a type of symmetric curve. Not all symmetric curves are normal, but all normal curves should be symmetric. Then within two standard deviations of the mean, we add an extra 13.5% of the data. So that means that if you add up all the percentages, 95% of the data should fall within two standard deviations of the mean. And then finally, within three standard deviations should be pretty much all of the data, because we add another 2.35%. So that means 99.7% of the data falls within three standard deviations of the mean, either above or below. So under a normal curve, you should only have about 0.3% at most of the data falling outside of three standard deviations. A z-value is just a more precise measurement of standard deviation. So we'll learn how to calculate a z-score, a z-value, by using a z-table. But this just, instead of being like one standard deviation above the mean, maybe you can be 1.57. You could figure out each individual element of data where it falls relative to the mean. If you have a positive z-value, that means you're above the mean. If you have a negative z-value, you are below the mean. This is how a z-value is calculated. We get the data value x minus, this is the symbol mu. It's a lowercase mu in the Greek alphabet. Mu starts with m, so think of that as the mean. And then you divide by the standard deviation in the set of data, which we learned how to calculate standard deviation by using online resources. Most of the time, they'll just give you the standard deviation. You won't have to calculate it. So the way that this z-table would be used, I have attached a z-table to your online class notebook. So the way that you would use this, let's see if I can navigate around here, is this tells you the area under the curve, or what percentage of the data falls to where you're looking and below. And this is not working here. Why isn't this scrolling? Let's try here. Let's try doing this. Maybe this will help. Okay. So let's say that I'm measuring people's heights, and I want to see what let's say that I'm able to get a big enough sample where all the heights are normal, and I want to measure what percentage of people I'm taller than. And my height ended up being, I need to calculate the z. So let's say my height ended up being 70 inches minus an average height of, let's say the average height was 67 inches, and there was a standard deviation in the set of data of, I don't know, let's say 2.38. So I would use my calculator to calculate what the z-value was for my height. My actual height is 70 inches, but I want to calculate what the z-value is, so I would go 70 minus 67 divided by 2.38, and that gives me approximately 1.26. So that's positive. So I'd want to go on my Z table to the positive values. See how I can navigate this thing. No. All right. The left side of the table are the negative values, and the right side are the positives. So see how these are negatives. So on the left side, the column going down, it goes up to the tenths place, and across the top is the hundredths place. So if I have a 1.26, I would want to find up to the tenths place, which is 1.2, which is here, 1.2, and then go across to the 0.06, because 1.2 plus 0.06 gives me 1.26. So if I look at the intersection where 1.2 meets up with 0.06, that gives me a percentage of 0.8962, or approximately around 90%. So I can say that my height, if this were the case, is roughly 90. I'm on the my height is about bigger than 90% of the rest of the population. If in this scenario, if these statistics were correct. I just made these up. I don't think I'm taller than 90% of the people of the population, but that's how a Z table works. So if you want access to this, this is available in the class notebook under forms. I suggest that you find it and even maybe print it out so that you can carry it around with you. Okay, so this is the Z table is used to calculate the area under the curve. It's also used to calculate probability. You can use it, if instead of measuring heights, I was measuring the chances of something happening. Whatever I was measuring, there was a 90% chance that it would occur. Again, based on what the Z table was saying. The way that you can calculate the error, if the statistic that you're measuring is an average, if you're measuring an average, the way that you could calculate your margin of error, your standard error, is to get the standard deviation and divide it by the square root of the sample size. However many people you're sampling, remember that statistic goes with sample, and parameter goes with population. So if you're whatever type of study you're doing, get the sample, take the square root, that goes in the denominator. On the top goes the standard deviation, and that would give you your standard error of mean, if what you're measuring is an average. If what you're measuring is a percentage, then the standard error of, in statistics they use this word proportion, but when you see proportion, just think percentage. So the way you would calculate one standard error, not to be confused with maximum error, that'll come in the next module, but the way you calculate standard error is as a decimal, you would put the percentage, so let's say 57% would be 0.57, times the complement of that percentage. So like if I was doing 57%, 1 minus 0.57 would be 0.43, so like 0.57 times 0.43 divided by your sample size, and then at the end take the square root of everything. Okay.